Students, hi, this is Mr. Bob, and in this video, we're going to walk through a sample problem involving a free body, an object moving, but with forces in both directions, and also with friction involved, okay? So notice for this problem, we're going to use G equals 10 meters per second squared for the sample problem, just to make the numbers a little easier. So I'll just quickly read the problem out loud. It says, Malia applies a 32 Newton force to the right to accelerate a 4.0 kilogram box horizontally across the floor. The coefficient of dynamic friction between the box and the floor is 0.30. Neglect air resistance. And there are 6 things you're being asked to do. One is draw a free body diagram. Second thing is fill in the forces table. Third thing is determine the magnitude of the normal force. Fourth thing, determine the magnitude of the friction force. Fifth thing, figure out the net force on the object. And sixth thing, determine the box's acceleration. So let's jump right into it. For part A, the free body diagram, we can assume, again, the box is a dot. We can reduce it to a point particle, so to speak. And then we're just going to kind of read the problem and walk through it. Malia applies a 32 Newton force to the right. That sounds like I have an applied force of 32 Newtons to the right. To accelerate a 4.0 kilogram box horizontally, that's going to be important later on, across the floor. The coefficient of dynamic friction between the box and the floor is 0.30. So the problem is telling me there is friction, and friction always opposes motion. So if the box is moving to the right, then the friction force has to be opposing that motion. That would be to the left. Neglect air resistance. Okay, now there are 2 other forces because this is on the surface of the Earth, and it's obviously the surfaces are touching, right? There's friction involved. So we know that there's the weight, force due to gravity, and then we also know that there is a normal force involved here. And it says neglect air resistance, which we typically do. All right, so we've done part A, check. Part B, fill in the forces table. In case you forgot, remember, this is the table where you kind of look at your drawing and you look at the sum of the forces in each direction, some of the forces in the x directions, and you just kind of list the forces. Before I do that, I just want to be really clear that I also have a coordinate system here that I have to make sure I'm very explicit about, and I'm just going to use the conventional right is positive, up is positive, down is negative, and to the left is negative, because that comes into play here. So now when I start listing my forces in my x direction, my horizontal direction, I have one force in the positive horizontal direction, that's the applied force. And I have a force in the negative direction, and that is the friction force. That's going to be minus the force of friction. Okay, in the vertical direction, in the positive vertical direction, I have the normal force. In the negative vertical direction, I have the force due to gravity. And down here, remember, this is where we list what the net force is, what we know about the net force. So in the x direction, we know it's accelerating. So we know it has some sort of mass and some sort of acceleration in the x direction, because the problem tells us that. What about in the y direction? Well, it just says the box is accelerating horizontally. So we can assume, since it tells us there's no change in its motion in the vertical direction, that the net force in the vertical direction is 0. Okay, so we've done part A and we've done part B. And let's just kind of to keep this thing organized, maybe make some boxes around this. Let's go to part C. Part C says determine the magnitude of the normal force. Well, notice this is where my forces table comes in very handy, because notice what I can do is I can just say, oh, well, let me write an equation for this. So notice these have to add up to be the net force. So in the y direction, the normal force minus the force due to gravity has to equal 0. That's what my forces table is telling me. So now it's just a matter of solving for the normal force. And I get that the normal force is equal to the force due to gravity, which we know is the mass times the acceleration due to gravity, which in this case is 4.0 kilograms times 10 meters per second squared. So the normal force is equal to 40 newtons. Some of you may be there thinking, oh, Mr. Bob, I kind of understood that already. You just look and you can just see it's got to be equal. That's great, but just know that these problems get more complicated. And that's why it's always good to kind of walk through the process methodically and then double check it with what you're thinking commonsensically. Okay, part D says determine the magnitude of the friction force. Okay, now you should have recently learned about friction, and remember the equation for friction is that the coefficient of friction, in this case dynamic friction, by the way, dynamic and kinetic friction are the same thing. Kinetic friction is more often talked about like an AP curriculum. Dynamic is what's often talked about in IB curriculum, but it's the same thing. The friction of moving objects. So the coefficient of dynamic friction is the friction force divided by the normal force. That's an equation that you have on your equation sheet. So what we need to do now is we need to solve for friction force, and we do that by multiplying both sides by the normal force. Okay, and when we do that, we get that the friction force is going to be equal to the coefficient of dynamic friction times the normal force. Coefficient is given to us as 0.30, and the normal force we found in part C to be 40 newtons. So when we multiply those two together, we get that the friction force is equal to 12 newtons. Okay, then B, C, and D. Moving on to letter E. Letter E says, what is the net force on the object? Okay, I'm going to do that one over here. Letter E. So we know half of the answer to this problem already, because the net force in the y direction we already said is 0. But what about the net force in the x direction? Well, let's go back to our forces table. Again, this is where this helps us out really, because the net force in the x direction, we can get that from this equation, that the applied force minus the friction force has to equal the net force in the x direction. So the applied force is 32 newtons from the problem. The friction force we just found in part D to be 12 newtons. So the difference between those two is going to equal the net force in the x direction. So the net force in the x direction comes out to be 20 newtons. Okay, I'm going to start boxing my answers just to kind of make them stand out. Okay, finally, letter F, the acceleration. Acceleration, when you think acceleration, these problems, think Newton's second law. Net force in the x direction equals mass times acceleration in the x direction. Solve for acceleration, divide both sides by the mass, and we get that the acceleration is going to depend on two things, the net force and the mass. The net force we just found to be 20 newtons. The mass is 4.0 kilograms. And so therefore we get that the acceleration in the x direction is 5 meters per second squared. Okay, so there you see in totality everything we've gone through. This is a sample problem for an object accelerating in one direction but feeling forces in multiple directions. And this is a good application of a lot of things we've been talking about. It will get more complicated from here. Eventually, we're going to start talking about inclined planes and other things. I hope you've enjoyed this video, and please have a good rest of your day.